record on this computer. Okay. All right, so Russell's paradox. So it used to be the case back before Zermelo and Frankel and other mathematicians like fixed the problems with set theory. It used to be the case that in like what they call naive set theory, sets were allowed to be elements of themselves. You could have a set S, which was equal to like the set containing like 1, 2, and S itself, right? So like in this situation, S would be a subset. No, sorry, S would be an element of itself, which is kind of weird, right? Because you can say like it creates essentially this like infinite recursion. Because you can be like, oh, what's a good example of this? A good example of this is new, which stands for new is not Unix. And this stands for new is not Unix. So you get new is not Unix is not Unix. Right? If you like sort of expand this set as a set, then it expands into something that contains itself, and you get this like infinite sort of recursive thing that like expands forever because it's self-referential, right? It's self-referring to itself. Does that make sense? Kind of weird, right? But yeah, so that's like, that was allowed, right? And so you can have a set be an element of itself. And so then Russell was like, all right, well, if I can do that, this is Bertrand Russell, mathematician. This happened right around 1900, right around the turn of the century. Bertrand Russell said, if I can do that, then I can define a set like this. The set S is going to be defined as the set of all sets X. So X is a set. And also, like, there was this idea of like the universal set of all sets. Okay, so take all the elements X, which are sets, such that X is not an element of itself. Okay, so the way truth sets work, the way this like, and I'm assuming you've watched the videos in 2.1. The way truth sets work, anything that satisfies that condition is by definition in this set. And it's only in this set if it satisfies that condition. So it's like an if and only if. This is the set that contains exactly all the things that satisfy that condition. That they are not elements of, oh, I'm sorry, I wrote this wrong, I apologize. That's supposed to be, they are not elements of themselves, what I meant to write, sorry. So it's the set of all sets that are not elements of themselves. So then the question is, it produces the paradox. Is S, this set which we've just defined this way, is this an element of itself? Thoughts on that? I know I'm recording right now, so it's okay if you don't want to. Well, here's the thing. We've got two cases. Either it is or it isn't, right? So if S is an element of S, well, then it's not an element, right? It's not an element of itself. So therefore, it shouldn't be an element of itself, right? Because the set of, this is defined as the set of all sets that are not elements of themselves, right? And it can only contain things that are not elements of itself, right? There's no other, like it can't contain anything that doesn't satisfy that condition. So this does not satisfy that condition, and therefore S can't be an element of this set. But as you can see, what I just wrote there is a contradiction. If it is an element of itself, then it isn't an element of itself, right? Contradiction. That possibility is not going to work. What about the other possibility? The other possibility is that it is not an element of itself. If S is not an element of S, well, then it does satisfy this condition. And this is supposed to be defined as the set of all sets that are not elements of themselves. And so if you have any set that satisfies that, it's got to be in there. It's got to be in that collection. So S is not an element. If it's not an element of itself, then it is. By definition, it is an element of itself, which likewise is the same contradiction, right? So either way, you have a contradiction. This is why this is a paradox. This is a true paradox. A lot of things that people call paradoxes are not true paradoxes. They're just like surprising facts. And that's not a real paradox. A real paradox is something which is like, literally leads to a contradiction. And so when mathematicians realized that the set axioms they were using as the foundation for all mathematics, when they realized that those set axioms allowed for this contradiction, they led to they allowed this to be considered this to exist. They were like, shit, that's a problem. because let me see if I can explain why exactly that's a problem. It's because it's because of vacuous truth, really. There's this idea in math called explosion, which is that if you can deduce something false, then from false, you can conclude anything. Like if your system creates something which is contradictory, then from a contradiction, you can conclude literally anything because it's vacuously true. And so the problem is, people were saying our axioms have an inherent contradiction among them. So anything that we've concluded from those axioms could actually be false, because you can conclude anything from a contradiction. And so it's kind of like people talk about you divide by zero and the world explodes. That kind of comes from this idea of explosion. Like it's kind of like if you had a computer that was generating all true facts from other known true facts, then as soon as it arrives at a contradiction, then it can just explode and generate literally every statement in the universe, because anything can be derived from a contradiction. That's kind of the logical fallacy or the logical problem there. So yeah, so that's Russell's paradox. Its significance was that, it caused this complete upheaval and chaos and sort of strife in the mathematical community, where people were like, oh no, there's a problem, we need to fix this right now, otherwise everything is meaningless. And so they did, and it only took them about 20 years, which is a relatively short amount of time in the world of math. So about 1920, Zermelo and Frankel presented independently, they kind of worked on it and ended up coming up with this new set of axioms, and now they fixed the problem and now it works fine. Okay, I'm gonna stop recording.